vector. So proof. We assume that our assumption is that this is not zero. This partial derivative of capital F with respect to y at the point AB is not zero. Okay, so without loss of generality, we can assume that this is positive. So we assume that since it is not zero, we might assume that it is positive. The case that it is negative can be proved similarly. Okay. Now, by continuity, because our capital F is C1, capital F is C1. This is the assumption. Why we need it to be C1? We want the partial derivative to be continuous. Okay. So using the continuity, we can find a low positive such that the partial derivative remains positive for point near AB. For xy near AB. Near AB, so it means that A minus rho, A plus rho. In this closed rectangle, if rho is small, rho small means that the point in this rectangle is close to AB. Now, this rectangle consists of this rectangle is centered at AB. Therefore, the rho is small. Actually, this is a square. Okay, the length of the side of the square is 2 rho. So rho is a square means that the rectangle is small. So the point in the rectangle is close to the center. That is AB. So because the partial derivative is positive at AB, it is positive at nearby points. So we have such a root. And also, this function, I don't need to write so complicated. This function dxf over dyf is continuous when the above rectangle, say denoted by R. Maybe I will denote this by R. Okay. So why it is continuous? Because both the partial derivative with respect to x and with respect to y are continuous, and the denominator will never be zero. Okay, therefore the quotient is also continuous. Okay, so since this is continuous and R is a sequentially compact set because it is closed and bounded, so this number the supplement of xy in, maybe I don't want to write, the supplement of R for this dxf over dyf is finite. This continuous function over the sequentially compact set R is bounded. Of course, the absolute value is bounded. Okay, so such a supplement we denoted by capital M, then capital M could not be infinity. Capital N is a finite number, no negative finite number. Now, we also have capital FAB is 0. And this partial derivative is positive. Okay, for y in this interval, b minus rho, b plus rho. What this means? This means the function y, the value fay, the derivative of this function y, the derivative of this function is precisely the partial derivative of capital F, but that is positive. So the derivative of this function is positive, strictly positive. Therefore, this function is strictly increasing on the interval b minus rho, b plus rho. Okay, so when y equal to b, this function is 0, fab is 0. So we see that the value of this function, at b minus rho is less than the value at b, but at b fab is 0, which is 0, and then this value will be less than a b plus rho. Okay, so we have this conclusion. This is the first step. Now this function x map to capital F x b plus or minus rho are also continuous. This function positive, these two functions, the value of this function at x is capital F x b plus rho or b minus rho. These are two functions. Okay, these two functions are all continuous. So and the value of this function at a is negative or positive. Okay, so by the continuity, there exists r positive, such that f x b minus rho is negative, and the f x b plus rho is positive for every x near a. That is x in the R neighborhood of a. Okay. So this is our preparation. Now, given x in this interval, this function will be denoted by psi y to be fxy. X is given, the y is changed. So for every different y, fxy is a real number dependent on y. Therefore, this is a function of y. We denote by psi. We have the partial the derivative of psi. That is the partial derivative of capital F at the point xy. This is positive. Okay, because our partial derivative is positive in the rectangle centering at AB, and which is side length 2 rho here. Here, the partial derivative is positive on the rectangle R. So fix x and let y change. So this is positive for y. Y is in the this is true for y in the interval b minus rho, b plus rho. So this psi is strictly increasing. Psi is strictly increasing, and psi a minus r rho, psi b minus rho is negative. This number, this is psi b minus rho, right? By the definition of psi, you see that capital F x b minus rho is psi b minus rho. This is negative. And similarly, psi the value of psi at b plus rho is positive. So this psi is a function defined in the interval b minus rho, b plus rho. The value of psi at the endpoints of the interval has different sign. One side is positive, the other side is negative. But psi is differentiable, and of course it is continuous. So it must have a 0 point in the interval. So we conclude that there exists a unique y. There exists a unique y in the interval b minus rho, b plus rho, such that psi y is 0. Okay? Psi is continuously differentiable under closed interval b minus rho, b plus rho, and the value of psi at the endpoints of the interval has opposite sign, so it must have a 0 point in the interval. Okay, so we get this y. Of course, this y depends on x, because our function psi is given from our capital F by fixed the first variable x. So for different x, actually the function psi is different. So the 0 point of the psi is also different. Therefore, the 0 point of psi depends on x. So this y can be considered as a function of x. Okay, so in conclusion, we obtained a unique y in the interval b minus rho, b plus rho, such that capital Fxy, that is our psi y, is 0. The 0 point, the existence of 0 point for psi is come from the property that the continuous function psi has different sign, opposite sign on the endpoint of the interval. The uniqueness of the 0 point y comes from the strictly increasing property of psi. Strictly increasing. If it is increasing but not strictly, maybe it has more than 1 0 point. But since it is strictly increasing, the 0 point y is unique and depends on x. This 0 point depends on x. So we denote this by phi x. Denote this y by phi x. Then the above discussion says that for any x in the interval a minus r, a plus r, for any x in the interval, we have a y. We have a unique y that is denoted by phi x, so that fxy is fx phi x equals 0, and also phi a is b, because fa phi a is 0, fa b is also 0. So by the uniqueness, phi a must be b. Okay. So phi a is b. This is easy. So we obtain a function. For every x you get a y. So this means we have a function. Okay. We get a function. Phi defined in the interval a minus r, a plus r, real valued, such that phi a is b. Capital F x phi x is 0 for any x in the interval.